Okay, close them up for a sec. I'm gonna just review something real quick, and then, so here's the plan. So there's gonna be, we're gonna go back to the compound transformation stuff. Here's kind of our plan for the next few days. So there's another assignment that I'm trying to get up. There's been some glitches on it, but I think I got it all worked out, so that should go up today. That'll be, so I'm adding, it's nothing new, it's just kind of more practice on this stuff. So I'm gonna look at a couple of those problems, and then let you work on this stuff. Tomorrow, I'm here through, I think, it's normally big for basketball. I think it's 10:25.
Yeah.
10:25, but we're released at 10:15, I think. Pretty sure.
I thought we were released at first week.
Maybe it is, I hope it is, but it might be a little bit early. So anyway, tomorrow what I wanna do is I wanna get you guys set up before we head out. I wanna get you guys set up to look at horizontal dilations. And that's kind of an honors only topic. It's not something we're gonna go through with the regular algebra twos, but for you guys, it's something you wanna take a look at. And then there'll be sort of a corresponding assignments up there for you to practice that a little bit before we move on to the rest of it. So we're gonna take one day, kind of catch our breath, just focus on the stuff we've been working on, and then tomorrow we'll extend that to what's a dilation again, vertical stretch or compression. Right now is what we've got, vertical dilations. What do you suppose a horizontal dilation is gonna be? Sideways stretch or compression, right? So we gotta look at that also. All right, but for now, real quick, let's just take a look at one of these guys, and we've been a few days since we talked about this. So how are we gonna do this? And how about,
Are you recording?
I am recording, yep. Thank you for asking. That's important to do, because otherwise I will forget a lot of the time.
It's your job. What did you do?
Why did the curse of the Can I make a guess?
On this one?
Yeah, no, for the stretching.
For the horizontal, you mean? Well, tomorrow you can. Yeah, tomorrow you can. I don't want to take the time today. I want to let you guys work. Okay, so let's talk about this one real quick then. So we're going to think about this in a couple ways. So what do? Okay, we can.
We can.
We can do that.
We can also do the,
We talked about on Friday, I think, right? We talked about how we could either, we can separate the horizontal and the vertical stuff completely, right? What we'd have to do, what we talked about doing first with this though, before we did the vertical, we have the option of doing the horizontal translation first if we want to, right? So what's our parent graph going to look like? It's going to look like a parabola. Good. So we've got the parent graph is going to be just plain old y equals x squared, and that's going to happen. Let's make an x-axis here. So, okay, so So here's my parent graph. The origin's gonna be at 0, 0, and what are some key points it goes through? 1, 1, 2, 4, 3, 9, and so on, right? And then it's gonna do the same thing on that side, right? So what are the transformations we're gonna make to this thing? we have the option of, I want to, let's go ahead and click all those things closed though. I'm not seeing everybody's focus up here, because I'm gonna do something a little different today. We're gonna look at this in an improved way. So we could scoot this thing, which direction? Right by 2 if we want to, that's fine, right? We have that option. What would we do next then? No, we can't do that. We can't go down 1 until we do what first?
Squish.
We've got to squish first. Now, what I'm going to encourage you to do here is let's do all the squishing first, okay? And then we'll do the translation. And here's why. If we rewrite this, f of x is just a fancy name for y, isn't it? Right? So let's rewrite this for a second using a y. So I've got y equals 2/5 times the quantity x minus 2 squared minus 1, right? Let's go ahead and add 1 to both sides. And then we're going to get something like y plus 1. You don't have to do it this way, but I just want to defend why I think it's important to do all the squishing and stretching first before you translate. Okay, so if we do that, this x minus 2, that's the part that tells us to slide to the right by 2, correct? Okay. Well, if I put that in parentheses, that's the same thing as saying y minus -1, right? So if we wanted to, we could set up our transformation equation. Instead of writing it like this, instead of writing f of x equals a times the quantity, not even make this specific. Let's just say we've got some parent graph, right? And we're going to write f of x in terms of a parent graph. Instead of writing a times p of, a times p of x minus h plus k, well, we could even write that if we wanted to as y minus k equals a times p of x minus h, right? And then doesn't this just look like that's mirrored to this side, right? This tells us we're going to scoot h horizontally, and this tells us we're going to take our original y coordinate and we're going to scoot k vertically, right? Everybody see that? And so if we look at it like this, it makes the most sense to distort the graph first, get an answer, and then all we have to do is just apply these simple translations to the distorted graph, right? Everybody get that? It's like we're not even paying attention to that part. We've just got y equals a times some function. So the a is going to warp the graph, and then we'll look at this and say, okay, well, we're just going to replace x with x minus h, which just means that we're going to scoot this thing horizontally by a prescribed amount. We're just going to replace the y with a y minus k, which means we're going to slide this thing vertically some amount based on k. Yes?
But if you move it over, wouldn't that change which way it's moving up and down?
Well, no, because what's the value of k here?
1.
Well, -1, isn't it? Right? What's the value of k here? No.
Minus -1.
It's because you're subtracting k from y, so it's still -1. See what I'm saying? Because look, we have y minus k, not y plus k, right? We're always going to subtract the amount from the variable corresponding to how far it's going to slide, right? So if we subtract a -1, it means we're sliding it in the negative direction. Well, vertically, what's the negative direction? Down, right? Everybody get that? So now you don't have to write it that way. You can still keep it like this if you want to, but I just want you to see that if we wrote it like this, then we're treating the x translations and the y translations the same, right? We're just going to subtract from the variable, directly from the variable, the amount that they're being translated, right? So when you think of it like that, which really makes more sense because it's treating both translations in the same way, we're just replacing the original variable with something like x minus 2, which just means, oh, okay, well, we're just scooting it, right?
But that always means that we're gonna do this part first, right? So let's go back to the problem then. Well, the problem here is, it looks like the vertical dilation factor is 2/5, right? So we've got our original parent graph. What do we do to that if we're multiplying by 2/5? What's a convenient point to pick? I guess we didn't even get that far out there. But it'd be the point that's way up there, right? That has coordinates, it's gonna be way up there. It's gonna have coordinates 5, 25, way up there. And we're going to multiply the y component by 2/5, and what do we get? 10. So we're gonna go over 5, and we're gonna go up, instead of going up 25, we just go up 10, right? So I don't know if I even could go that far. 1, 2, 3, 4, 5, 6. There we go, right there, right? So there's gonna be that point, and this thing's gonna get squished down quite a bit then, isn't it? Instead of going up 1, I'd only go up 2/5, so I'll try to estimate that. Instead of going up 4, I'm gonna go up 2/5 of 4, which is 8/5, right? So what is that, 1 3/5, so something like that. And we get an idea that this thing's been squished quite a bit. Right, so there's our squished graph, and now that we've got the squished graph, now we can do the translation. So we're gonna go down 1, and right by 2. So we'll drag this whole thing, right by 2 and down by 1, and that's where it ends up. It's gonna be a wide graph that's been squished that has a vertex there. Right? Yes, ma'am?
What's the, and like the y minus k equals a times b, what's the p?
Oh, that's just the parent graph, right?
Okay.
So for us, it was x squared, right? But I wrote it this way. I wrote it this way so we could just be totally general. So p of x could be anything. It could be absolute value, could be square, could be a quadratic, could be cubic, could be anything, right? But this just tells us that regardless of what p of x is, the three things that we're doing are we're vertically dilating, and then we're just translating it horizontally and vertically by some amount. Okay? Does that make sense? Okay? So let's try one more of these. So the other thing I'm going to have you do is I'm going to have you reverse that process. Okay? I guess I get these backwards, but that's all right. Let's do one of these where I give you, I'm going to give you the graph, and you have to write the function.
Okay.
So something like this.
Why can't you be weight loss on Why can't you just use weight loss on
Okay, here we go. Something like this, right? So here I gave you a graph. Now you gotta write it in this form, right? So you really all you're doing is you're gonna pick the values. You have to extract from the graph the values of the vertical dilation factor and then h and k. H and k are easy. What are h and k?
Up and down and left and right.
So what are they? So what are the values based on that graph right now? What are the values of h and k?
-4 is k.
K is -4, h is -3, and that's really easy to track because there's the special point. That's the vertex. it started there, right, and it ended up there. So all we have to do is just look at its final coordinates, and those are h and k, aren't they? Right, so we know right away that hk equals -3, -4, right? The only thing we really have to do here that's at all challenging is we've got to figure out how much did we squish or stretch this thing vertically, right? And so now, to do that, we're just going to ignore the translation for a moment, right? So we're just going to assume, and you don't have to regraph this or anything, just think of it this way. Think of it this way in your head. Just imagine that that's the origin, right? So if that's the origin, so I'm gonna specifically like redraw the x and y axes here, but you don't have to, right? If that's the origin, then here is a point on the graph. That's a squished or a stretched point. Squished. Okay, where would it normally be? If I go over 2, I would normally do what? I'd go up 4, right? So normally it would be up there. So if I've gone from being up 4 to being up 1, what did I have to multiply the y values to go from a y value of 4 to a y value of 1? Yeah, I just multiply by 1/4. Now, how could I turn that into kind of a, that's pretty easy, that's a pretty nice, easy calculation. But what if those were bizarre numbers? Like what if that was a 7 and that was a 3? How could I come up with a sort of an algorithm here that I could always use? If I want to find out what the vertical dilation factor is, what could I always do? If this is the final value and that's the initial value, and I multiplied by the vertical dilation factor to get the final value, and I could set that up as an equation, right? I could just say that the original value 4 times a has to equal the final value. I just solve for a. Right? Divide both sides by 4, and I would just get a equals 1/4. And you probably already see that, wow, a is always just going to be the final y value divided by the initial y value, right? If I haven't translated it first, if I'm starting at the origin. Everybody see that? Okay, so then my answer would just be, if I want to write this out in this form, and I'm filling in the blanks, f of x just equals 1/4 times the quantity x minus -3, so that's x plus 3 squared, plus k, which is -4, right? Everybody see that? And if I wanted to write it in that other way that I showed you, which we don't, I could write this as y plus 4 equals 1/4 times x plus 3 squared, right? Which just means that we started with, if we start with y equals 1/4 x squared, so we start with just the dilated version, then all I'm going to do is I'm just going to replace the y with a y plus 4, which shifts it down by 4, right? And I replace the x with an x plus 3, which shifts it left by 3. Okay, you get the idea? Okay. All right, so you can work. I'm going to put up that other assignment. Tomorrow we'll add the horizontal stuff.